Unmute.
Okay.
Okay, the next talk of the session is by Roshan on Blackbox principal minor assignment.
Yeah. So this is joint work with Abhiram Aravind, Abhranil Chatterjee, Sumanta Ghosh, Rohit Gurjar and Chandan Saha. Rohit is also here in the audience. So first I will define what are principal minors. For a submatrix A, if we take same subset of rows and columns, then we get principal submatrix for that set S. And when we take its determinant, it is called its principal minor. So, okay, here is an example. So this is this 3 cross 3 matrix, and following is the list of all of its principal minors. And principal minors corresponding to the singletons are just the diagonal elements. And suppose if we take this set 1 3, then the submatrix in orange is the corresponding principal submatrix, and its principal minor is 4. So the problem of principal minor assignment, we are given oracle access to the principal minors of an unknown matrix, and the goal is to find a matrix which has same principal minors. So like for this example, we will be given oracle access to this list, and we have to generate a matrix A or something equivalent to it. So, and we have to, the goal is to do it in polynomial time. So for, like I told, for this same input we can have more than one matrices. So here is another example of this matrix which has same principal minors as that of A. So here is an application of this problem to determinantal point processes. So a determinantal point process is a probability distribution model over some subsets of a ground set, and the probabilities are exactly the principal minors of a matrix, for positive semi-definite matrix called kernel. And to ensure that like this is a valid probability distribution, there is one more condition, that identity matrix minus this K should also be a positive semi-definite matrix. So here we get like some intuition about what are these entries of these kernel matrices. So if we consider 2 cross 2 principal minors, which from the definition is like a probability that 2 elements are picked in the random set, that is equal to product of the product of the individual probabilities minus this square of the matrix entry corresponding to this pair. So this shows that here the elements are negatively correlated, and this matrix entries is like a measure of negative association. And this is one of the reasons this is used in recommender systems. And there are some a related learning problem for DBPs is to learn this kernel by sampling subsets of the ground set. And there is one result by Urshel, Brunel, Moitra and Rigolet that first learns the principal minors of the kernel matrix, and then from sampling, and then uses this kernel to solve this to find this kernel of this matrix, and which then uses a result for principal minor assignment problem for symmetric matrices by Racing, Kulej and Tashkar. So here is another view of this principal minor assignment problem. So suppose this is the input matrix A, and X is the diagonal matrix whose entries are distinct variables. And now we will look at this polynomial determinant of A plus X. And if we look at, since all the entries appear at most once, this is a multilinear polynomial. and the coefficient of product of variables present in this set is exactly equal to the principal minor corresponding to the complement of that set. For example, if we take the product of these variables from x2 to xn, its coefficient will be the first diagonal entry of this matrix A. So different view of PMAP is that we are given access to the coefficients of determinant of A plus x, and the goal is to find a matrix A. So inspired from this, we can define a black box version of this problem, where we are given access to the evaluations of determinant of A plus x, and the goal is to find this matrix, unknown matrix A. And this problem is easier than PMAP because given evaluation oracle, we can always compute principal minors. How can we do that? So suppose we have to find the principal minors for a subset S, then we will substitute all those variables to 0, and the variables which are not present in this set S, we will substitute by a fixed variable, univariate variable, that is t, and then the maximum degree of that determinant of A plus x will be the principal minor for that set S, and that we can compute using interpolation by making at most n queries. So this is an easier problem. Now I will mention a more general problem. So here we are learning a class of polynomials which can be computed by a symbolic determinant of matrix that looks like this. Here the constraints is that the matrix coefficients have rank at most 1. So like A1, A2 and AN can have rank at most 1, and there is no constant on this constant matrix which is A0. We are given black box access to this function, this polynomial f, and the goal is to learn these matrices A0 and rank 1 matrices AIs. So this symbolic matrix A plus x is such an example. When we separate this, when we write this diagonal matrix capital X into, when we decompose this, we get these matrices, and note that here the coefficient of these matrices are diagonal matrices with only one non-zero entry, hence it has rank 1. And this class of polynomial has applications, captures many problems like bipartite matching and linear matroid intersection, and it also generalizes read-once formulas. Now I will mention what are our results. So our first result is that we give a randomized polynomial time algorithm for black box principal minor assignment problem. And this we do in 2 steps. First we show that this black box principal minor assignment problem reduces to PMAP for a special class of matrices, and this special class consists of dense matrices. By dense matrix we mean that all of the off diagonal entries are non-zero, and it has some property which we call rank 1 extension property, which I will define in the next slide. And one note is that this is the only part where we use randomization, and in the second part we shows that we can learn the principal minors of dense matrices with this rank 1 extension property using only principal minors of order up to 4. And the next theorem is that we show that this learning symbolic matrices with rank 1 coefficients reduces to black box principal minor assignment problem. So as a result of this, we get a randomized polynomial time algorithm for learning symbolic determinants with rank 1 coefficients. In this talk, I will only talk about this first theorem and these 2 steps. So first I will define what is this rank 1 extension property. So this statement just says that a matrix has this rank 1 extension property if any 2 cross 2 submatrix with disjoint rows and columns has rank 1, then we can extend this submatrix and get a bigger submatrix that contains the original submatrix, and it has rank 1, and also the row indices and column indices should cover the whole index set. So here is an example. So this is a 5 cross 5 matrix, and here is a 2 cross 2 matrix with of rank 1. Note that its column indices are 3, 4, and row indices are 1, 2. These are disjoint. We can extend this and get this another submatrix which contains this smaller submatrix. It also has rank 1, and it covers the whole index set. And we can do this for every 2 cross 2 submatrix which has rank 1 and disjoint rows and column indices. So, but suppose if we change this entry to 2, now there is only 2 possible extension of this submatrix. The earlier one, that choice is gone now, and the another choice is that we add this row, 5th row. But here also again this rank is not 1, so this does not has rank 1 extension property. Now I will talk about the first part of the result, first step of our algorithm, that is reducing Black-Box PMAP to special case of PMAP which has this rank 1 extension property. And for that, first we do some pre-processing, and in this pre-processing we convert this we first convert this input matrix to be some irreducible matrix, and for that I will define what are irreducible matrices. So a matrix is called reducible if we can permute its rows and columns simultaneously to get a block upper triangular matrix. So in this example, if we exchange second row and second column with third row and third column, then we get this block upper triangular matrix. Another way to look at this is by considering this matrix on this graph on 4 vertices, where there is an edge between 2 vertices I and j if the entry in ith row and jth column is non-zero. For example, in this matrix, the entry in the first row and second column is non-zero. That's why there is an edge from 1 to 2. However, the matrix entry in the second row and first column is 0. That's why there is no one backward edge. And now this strongly connected components of this graph exactly correspond to the irreducible blocks of this matrix. For this kind of matrices, so like we said, we can it can be written as this block upper triangular form. If we see its this symbolic determinant, then it factorizes into 2 parts of similar forms. So this is because a principal minor of any submatrix which is contained in A, it will be covered by this first part, and principal minor of any submatrix which is contained in this A2, it will be contained in this part, and any principal submatrix which contains both of this, which comes from A1 and both A2, then it is just product of some principal minor of A1 and A2, and so that's why this captures this. AT does not play any role because it does not take part in principal minor of any of these submatrices. So now, using Black-Box factorization algorithm, we can assume that we have evaluation oracles for each of these factors, and hence we can assume that our input matrix is an irreducible matrix. Now, from irreducible matrix, we now convert it into a matrix which is dense and satisfies this rank 1 extension property, and this directly follows from a lemma of result by Hartfield and Louis from the 80s, and another result of our result of last year, which says that if a matrix A is irreducible, and then we consider this matrix A plus X inverse, then it is dense and it satisfies this rank 1 extension property. So now, but this is a matrix over with rational functions as its entries. So it's not easy to work with. So we put some random diagonal matrix, and we claim that it is also again dense and has this rank 1 extension property. So first we have to show that it is dense. This is because now we know that the matrix entries are non-zero. So, and if we take a random substitution for these variables, then from Schwarzschild lemma we know that this rational function will be non-zero. So hence we get all the entries of a plus d inverse is also non-zero. So for each entry we get some instance of PIT. And now the second part is that we have to argue that it has this rank 1 extension property. And for that we will ensure that whatever some matrices in A plus X inverse has rank 1, it will also have rank 1 in this A plus D inverse. And that we can ensure by arguing that every 2 cross 2 some matrix in A plus X inverse that has rank 2, it will again have rank 2 because it is again a PIT instance with n, at most n number of variables and degree also not very large. So there can be at most n raised to 4 many PIT instances, and so a random substitution will make each of these PIT instances to be non-zero. So at the end we get a matrix that is dense and satisfies this rank 1 extension property. Now we have I claim that this reduces to an instance of principal minor assignment problem. So we also have to get principal minor oracle for this A plus D inverse, and which we can get from this using Jacobi's identity, which relates the principal minors of an inverse of a matrix and the original matrix. So this completes the first step, that is reduction of Black-Box PMAP to a special case of principal minor assignment problem. Now I will talk about the second step, for which I will take a slight detour and talk about a related problem of principal minor equivalence, which says that given two matrices A and B, we say that they are principal minor equivalent if they have same principal if all their principal minors are same. So like for one example is that if we take transpose of a matrix, we get another matrix that has same principal minors. This is because just determinant of a matrix is same to the determinant of its transpose. And one another simple operation we can do to preserve principal minor is that we can multiply first row by some non-zero scalar and simultaneously divide the first column by that scalar. So why does not change any principal minor? Because first of all, the rows and columns from 2 to n are not changed, so that any principal submatrix that is contained in it is not changed. And for the principal minors that contains first row and first column, when we expand their determinant, d and 1 by d cancels each other out in each term of the determinant. So we do not change the principal minors. So we can do this operation simultaneously to multiple rows and columns, and this will be captured by multiplying this input matrix A with some invertible diagonal matrix on left hand side and simultaneously dividing it by its inverse on the right hand side. Such a matrix is called diagonally similar to the input matrix. So here is an example that we saw in the first slide. We saw that these two matrices have same principal minors, and this is because B is diagonally similar to A. Yeah. Now I will mention some results on principal minor equivalence. For that I have to define what is called a cut of a matrix. A subset S of the index set is called cut if it has size at least 2 and size at most n minus 2, such that these two submatrices have rank 1. What are these submatrices? We take the rows indexed by set S and columns which are not in S, and vice versa, we take columns which are in S and rows which are not in S, and both of them should have rank 1. So here is an example. So we consider this set 1, 2, then these two sum matrices are presented in this red sum matrices, and both of them have rank 1 because there is only one non-zero entry. However, if we see another set like 1, 3, 4, then this second sum matrix is given in this orange, and we can see that it does not have rank 1, so this is not a cut. In this slide, I will talk about some results known for principal minor equivalence for matrices which have some constraints. This first result is by Hartfield and Lowy, which show that if a matrix is irreducible and does not have any cuts, then another matrix B has same principal minors if and only if it is diagonally similar to A or its transpose. So the two matrix operations that preserve principal minors that I mentioned in the previous slide, that are sufficient to describe any principal minor, that is any matrix that has same principal minors as of A. So this here is a corollary of this theorem. This says that for a given matrix A, if it has dense, then there is only two possible matrices whose off diagonal entries in the first row are all ones. So this is because if we fix all the off diagonal entries in first row to be 1, this fixes the diagonal matrices D, and there are two choices, so that's why we will get we get only two principal minor equivalent matrices with this property. This is another result we show in our current paper. We show that a matrix A which is dense and has this rank 1 extension property, for that another matrix B has same principal minor if and only if they have same principal minors up to size 4. So we don't have to check all principal minors if we just have we just have to check principal minors up to size 4. That is enough to say that another matrix B has same principal minors as of A or not. Now we use these two results to give an algorithm for principal minor assignment for matrices with which are dense and satisfy this rank 1 extension property. In this talk, I will talk about a very special subcase which says that this input matrix is dense and all its 2 cross 2 sum matrices has rank 2. So note that this is also the property satisfied by any random matrix with high probability. So because this 2 cross 2 sum matrix, it will have determinant non-zero, so that's why it will have rank 2. So what does this property ensure? This ensures that since there are no sum matrices with rank 1, it does not have a cut, and also it automatically satisfies this rank 1 extension property. Since A does not have a cut, there are only two possible choices for another matrix B which has same principal minors, and that follows from a result of Hartfield and Lowy. So this is, now I will describe the algorithm. So suppose this is the matrix that we have to learn, and right now it's empty, and we will fill it gradually, and whatever entries that we have learnt, we will color it with red. So first we will learn the diagonal entries by just querying principal minors corresponding to singletons, and like I mentioned in the previous slide, without loss of generality we can assume that the off diagonal entries in the first row are all ones, so we will directly just assume that they are all ones. And now we will learn the entries in the first columns. For that we will consider principal minors for sets of size 2 which contains this first row and column. So suppose we consider this sum matrix. We know 3 entries. We have to learn only this, that we can learn using querying this principal sum matrix. So similarly we learn all the entries in the first column. And one important point is here is that any submatrix of this matrix also satisfies this property that that it is dense and has all its 2x2 submatrices as rank 2. So we will follow an inductive algorithm, and we assume that suppose we have learned some matrix which is principal minor equivalent to this submatrix. So now we have to only learn this last row and last column. So we'll start with this first empty entry. For this we consider set of size 3 that contains this second entry and this last row and column. So this is a 3 cross 3 matrix and it is dense. So from Hartfield and Lewis result it has all ones in their off diagonal entries. So there are only 2 possible choices. And we will try both of these choices and match the entries with whatever matrix which has learned. One of them should be the correct choice. So we have learned these 2 cells. Now we will go on, we will use this approach and keep learning this last row and column. So suppose at some instance we have learnt up to this, and we have ensured that the principal minor corresponding to this set S minus K, and we have already learnt correctly, and now we have to learn this entries in the kth row and kth column. So one thing is that if we learn any one of these entries, we automatically get the second one by considering the principal minor of K and N corresponding to set K and N. So how do we do that? Again, we take a submatrix which contains K, and we take another submatrix which does not contain K. And from our inductive hypothesis, we know that one of these choices should be correct here, and one of these choices should be correct here. So we'll try all these 4 choices, and now query. And now we know that this matrix has rank 1 extension property. So we only have to check 4 cross 4 principal minors for each of these 4 choices, and whichever choice is valid, we take any one of them, and that is the algorithm. And in the general case, in the general algorithm, everything is similar, but here we have to carefully choose how we induct. We cannot just arbitrarily choose any index and do induction, and that depends on at that point that is our main technical contribution, which I will not talk about. Okay, so this way we have learned all these matrix entries, and now I will list some open problems. So yeah, the first one is obvious, that is like can we solve principal minor assignment problem for general matrices? So here the main the problem got simpler because we have this oracle for A plus X inverse, but now if we want to do any query for this A plus X inverse or A plus D inverse, we cannot do that using polynomially many queries to the principal minor oracle. So we don't see how we can generalize our approach. Now second problem is related to algebraic geometry. There is this principal minor map which takes as input n cross n matrices and maps it to a 2n dimensional vector, 2 raised to n dimensional vector, such that its coordinates are principal minors, all the principal minors. Lin and Strumfels showed that this affine principal minor map is Euclidean closed, and they also gave up characteristic equations for matrices of size up to 4. And in the same year, Odin gave up characteristic equations for symmetric matrices. So a general question would be that can we give a set of characteristic equations for principal minor for general matrices? And the third open problem is related to learning sum of symbolic determinants with rank 1 coefficients, where these rank 1 coefficients have rank at most 1. Yeah. Thank you.
Hi. Are you aware of Griffiths and Satsumeris's work on principal minor assignment? I don't remember the details now, but I think they also look at, I think they look at the general case, and from what I remember, they gave a polynomial time algorithm. They also had this property that you only need to look up two minors of order 4, and then you can reconstruct, given the principal minors, you can reconstruct the entries of a matrix.
So I think they consider not general matrices. There are some.
I think they consider only field elements, from what I remember. I might be yeah. So
yeah, most probably I think they consider some different property. This is called ODF, I think.
Okay. Yeah. Now I think I remember. Something
Yeah.
like that. Yeah.
Yeah,
Okay.
but I think that is.
Okay. Thank you.
More questions?